Hey guys, in this video we're going to be going over how to convert decimal fractions to binary. If you haven't seen the previous video on decimal to binary, please check it out. The link for that will be in the description, and be sure you follow through that and make sure you understand what it is that I'm talking about in that video, because this is a continuation of that video. So one of the things that I mentioned in the previous video is that you should be familiar with your powers of 2. And here I've listed from 2 to the 0 up to 2 to the 10. So we'll briefly go through them real quick. So 2 to the 0 is 1, because anything to the 0 power is 1. 2 to the 1 is 2, and 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16. 2 to the 5 is 32. 2 to the 6 equals 64. 2 to the 7 equals 128. 2 to the 8 equals 256. 2 to the 9 equals 512. And 2 to the 10 equals 1024. Now you should notice a pattern here. You know, from any given number, let's say I'm trying to go from 2 to the 2nd to 2 to the 3rd, you just multiply the previous result by 2. Now it's important to keep in mind all these powers of 2 and be able to recall them quickly, because it makes converting a given decimal number to binary a lot simpler. So let's say, for example, we wanted to go from, or we wanted to know what 2 to the 6 was, and let's say all I knew was 2 to the 3. Well, 2 to the 6 is 2 to the 3 times 2 to the 3, and you know it's 8 times 8, which you can do pretty quick in your head, which is equal to 64, and you know you get the idea, so on and so forth. Okay, one of the things I wanted to look at was the method that I discussed previously, where I was stating that there is a way that you can come up with a given decimal value and like find its binary representation, and there's a way to do it without having to constantly divide that decimal representation by 2 and keep track of the remainders. And I believe this way is a little more intuitive, and you're less likely to make mistakes and then lose track of those remainders and you know get a totally incorrect result. So the method for that is you want to try to find a power of 2 that is less than this number. So for example, let's go through some of the powers of 2. We know 2 to the 2 is 4, 2 to the 3 is 8, and 2 to the 4 is 16. So since 2 to the 4 is 16, 16 is greater than 15, so we want to take the previous power of 2 and subtract it from the decimal number. So we're going to do 15 minus 2 to the 3. So it's 15 minus 8, which is equal to 7. And you continue this for 7. So we know that 2 to the 3 is 8, which is greater than 7. So we're going to do the previous power and subtract that from 15. So we'll do 15 minus 2 to the 2. So 7. 7 minus 2 to the 2. So 7 minus 2 to the 2, that's 7 minus 4, which is equal to 3. And then you do the same thing, and you should notice a pattern here. This result is going to be greater than what you get, so you're always going to do the previous one below that. So then on this next line we're going to do 3 minus 2 to the 1, which is equal to 1, and then 1 minus 2 to the 0, which is equal to 0. And once you hit 0, then you can stop. And keep in mind these placeholders. You know, 2 to the 3 goes to a given placeholder, 2 to the 2nd goes to a given placeholder. So once you know, recognize that and you remember where these powers fall, then you just write a 1 in that given placeholder. So for example, we'll start here on 2 to the 0. So 2 to the 0 is in this placeholder, 2 to the 1 is here, 2 to the 2nd here, and 2 to the 3 is there. The reason why we put 1 is because we actually, you know, use that given placeholder's value. We actually evaluated it and we subtracted it, you know, through here. And you just want to keep that in mind. You know, want to write that down every time you do that and keep track of its given placeholder. So based on this math that we just did and everything that we solved, we're saying that 15, you know, base 10 is equivalent to this in binary. And just to double check, you want to check your results just to ensure that what you did is correct. Okay, so we're going to check the result that we got in the previous slide. You know that whenever there's a 1 in a given placeholder, you want to add those values together. So we had 4 1s, previously, and I'll rewrite that just so you can see what I'm talking about. And each of these 1s corresponds to a given power. This is a power of 0, power of 1, power of 2, power of 3, and so on and so forth. And you want to add that result out. And right here I'm saying that 2 to the 3 plus 2 to the second plus 2 to the 1 plus 2 to the 0, does that equal 15, base 10? So let's evaluate that. 2 to the 3 is 8, 2 to the second is 4, 2 to the 1 is 2, and 2 to the 0 is 1. So 8 plus 4, that's 12, plus 2 is 14, plus 1 is in fact equal to 15. So we know that what we have, this binary representation here, is in fact the representation for 15 base 10. So with that method in mind, be sure to practice that a good couple of times. Be sure to make sure that you're given powers of 2 so you can quickly go through this result. Practice it a little bit, and after a while it'll become a lot more natural. Okay, so in order to do decimal fractions to binary, we're going to go over how you actually represent numbers in base 2 to the right of the decimal place. So far we know this, and you know that in this given placeholder in the 1's place, it starts at 2 to the 0, and then the further you go left, it's just going to keep increasing in power. And you might be wondering, what is it exactly that you do once you get to the right of the decimal place? Well, the power convention is similar, since we already have 2 to the 0 to the left of the decimal. Once you go to the right, now it's going to be 2 to the negative 1, 2 to the negative 2, and so on and so forth. And it's going to continue like that the farther right that you go past the decimal. And for those of you that don't know, 2 to the negative 1 can be rewritten as 1 over 2 to the 1. And 2 to the negative 2 can be written as 1 over 2 to the power of 2. And since we have 1 over a given power, that's going to give us a fraction. So for example, if we evaluate this, 1 over 2 is 0.5, and 1 over 2 to the second, which is 4, is going to be 0.25. And we'll look at how exactly you take a fraction and you evaluate it. I'm going to show you a method of doing that. Okay, so let's say, for example, we wanted to represent the let's say we wanted to do, let's say 0.625, base 10, and we want to know its binary equivalent. Okay, so one of the ways that you can figure out its binary equivalent, and it can be a little messy, but this is usually the way that it's initially taught. So in order to find out the binary equivalent, instead of dividing by 2, now that we have this could be represented as a fraction, now we want to multiply this decimal by 2. So let's go ahead and do that right now. So we have 0.625 times 2, and that equals 1.25. So one of the things that you want to keep in mind when you're doing this is you want to keep in mind the value that's before the decimal. and this is going to be, you're going to place this number in the given placeholder that you just evaluated it for. So right now we're evaluating for, like, the position 2 to the negative 1. So in that position, you're going to place a 1 there. And then what you do with this result right here after the decimal place is you take that result and you multiply by 2 again. So 0.25 times 2, that equals 0.5. And the same thing here, you have a 0 to the left of the decimal and 0.5 to the right. So you're going to place this 0 in the 2 to the negative 2 placeholder. And then now we're going to do 0.5 times 2, which is equal to 1.0. And this 1 is going to correspond to the 2 to the negative 3 placeholder. And since we have 0 here, multiplying by 2 isn't going to do anything, so we know that we can stop. So let's go ahead and write this out. I'm going to include the decimal just so you can see what I'm talking about. So we have 0 dot, and in the 2 to the negative 1 position, we stated here that we have a 1. In the 2 to the negative 2 placeholder, we have a 0, and in the 2 to the negative 3 placeholder, we have a 1. So this is the binary representation for 0.625. Let's look at another example, this time with one that includes a number that's a little bit harder to evaluate, so that we can hopefully cement the idea in your head. Okay, so let's look at another number. Let's say something like 5.75 base 10, and we want its binary representation. So what you want to do on these ones is that you want to break it up into parts. Evaluate the left part of the decimal and then the right part of the decimal, and then just put them together afterwards. It's a little easier that way, in my opinion. So let's say 5. You already know you can do 5 minus 2 to the 4, which equals 1. I'll do 1 minus 2 to 0, which equals 0. So the binary representation for 5 is going to be 1, 0, 1. Oh, no, I'm sorry. This is not 2 to the 4, this is 2 to the second. And 0. Okay, and then we're going to look at 0.75. And we can do the same method I stated before. 0.75 times 2, which equals 1.5. Keep in mind this. And this is for the 2 to the negative 1 placeholder. And then we do 0.5 times 2. This equals 1. 0.00. So there'll be a 1 here. So 0.75, the binary representation, is going to be, 0.11. And you can just, combine these results and it'll give you the representation for 5.75. So I'll go ahead and write that on the next slide. So 5.75 binary representation is 0101.11. And if you go through the math on this, you'll see that it is in fact 5.75. So this right here, 2 to the 0 plus 2 to the second is equal to 5. So this results 5. And we put the decimal place there, and then 1 over 2 is 0.5 plus 1 over 4 is 0.25, so that's 5.75. So that checks out. Well, I hope you learned something useful in this video. and be sure to go through this and practice these concepts that I went over. If anything doesn't make sense, please leave a comment below, and I'll try to get back to you as soon as I can. Or I can come up with a follow-up video to hopefully clarify any questions that a majority of the people might have. But have a good one, and until next time.